We start with a new chapter, as you notice, chapter 6, and that's the last chapter in this part on series. And the title of the chapter and also of this first section is Power Series. So, well, the word series, we know what is this power now. Well, this is now that where we're gonna not just have a series consisting of numbers, but a series consisting of containing a variable. So, let me give a simple example. Let's look at this series. 1 plus x squared plus x cubed plus x to the fourth plus... So far I've written down a polynomial of degree 4, but now the dot 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 says this kind of keeps going. And so a power series can also be said just as a polynomial of infinite degree, whatever that means. Infinite degree. That's just what it means. But you say, yeah, okay, but what does that now mean? Okay, if I have a polynomial, like say a simple polynomial, quadratic polynomial, 3x squared plus 5x plus 2, that's my polynomial, let's call it f of x. Now I can always plug in numbers now. In a polynomial you can plug in numbers, and in particular you can find the solutions of a polynomial. So if f of 1, what is that? Well, you plug in 1. 3 times 1 squared plus 5 times 1 plus 2, so that in this case is 10, right? And I can do whatever I want. Any number, it always will work. But if you have something that is infinitely many terms, if you're now going to plug in a 1, let's try to do this. Let's call this guy here. So let's get rid of this example of polynomials. So now imagine I have this guy, and let's give it a name, f of x. And I want to calculate f of 1. So what does that mean? Okay, that means I would replace x by 1. So I get 1 plus 1 plus 1 plus 1 plus dot 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 dot. Oh, that's impossible, right? So this would diverge. So we have now a bit strange thing. We have this thing which we call an infinite degree polynomial, a power series, but you cannot plug in a number. Well, no, I don't know whether you cannot plug in a number. Let's plug in 0. F of 0, that will work, right? Because everything else is 0 except for the very first term, so it's just 1. Okay, so 0 I can plug in, 1 I cannot plug in. Are there numbers that I perhaps might plug in? Because what happens if I plug in a number in here? Whatever it is, so let's do a half. If I plug in a half here, I get 1 plus a half squared, which was 1/4. What is this? Why is this doing this? 1/4 plus 1 half cubed, 1/8, a half to the power 4, 1/16, plus so on. And we kind of recognize this, right? This is what we called a geometric series. Okay, so it's a geometric series, and we know exactly what r is. R is a half here. And for the geometric series, the only thing what we needed was the absolute value of r less than 1, then we had convergent. So what we have written down here, in other words, is a convergence series. In this particular case, but this is, as we know already now, kind of unusual, we even know what it is, because we have a formula for it. The formula is a over 1 minus r. And in this case, a is the first element, 1, and r is what we have here. So this would be 1 over a half, which is 2. So in other words, what we have shown actually in this case is that the function f here, this power series, if I plug in a half, then I get a value 2. But in particular, so the fact that we have a value is actually not going to be something yet of our concern. Later we'll think about it more, but not now. What matters is that it converges. So plugging in 1 diverges, plugging in a half converges. What's the deal? Okay, and so this is now the general thing. So in general, a power series, what is a power series? Well, there are many ways of representing it. I wrote it here as 1 plus x squared plus with the dot dot dot. It's a little bit imprecise, the dot dot dot, because we don't know exactly what we mean, although everybody guesses it. So we have used this summation sign here, sigma sign, to write down what it would mean. In this case of a geometric series, we have kind of been used to doing this. It's we would represent it this way. And we start from 0 in this case. But so notice the difference is here now that we have an x in here, or rather a formula that depends on x. Okay? But that's what a power series is. So a power series will look like an x to the n, from n going from 0 to infinity. It doesn't have to be 0. We can start somewhere else, but for simplicity, I'll take 0 here. So notice that it has a coefficient here, the ans, and then this is the x, the variable part, like a polynomial would do with the same thing. We could write it out. If we don't like this summation sign, we could write it a0 plus a1x plus a2x squared plus and so on. Okay, that's a power series. Now, we need to be a little bit more general than just this. If we, with polynomials, we can always do this. But as you will see, we have to pay attention to something what is called the center. So the center of a power series is where you center the power series at. In this case, the center is, well, I'm not going to tell you what the center is in this case. I'm going to write down a more general case. So the case where the center is A, what is that? How does it look like? Well, we have, let me call the center C. It makes more sense, right? C for center, okay? So the center is C. What does that mean? Well, we have still these coefficients here, these coefficients in front of the power series ring. What were they in the first case? By the way, they were all 1 here, right? All these cases, everything was 1. But I could put other things there. Okay, so we have A, and now what is the difference with what I'm going to do here? Instead of powers of x, I'm going to look at powers of x minus c. So the center is where you kind of deviate from x. And this is something you might remember. We had this when we're doing Taylor polynomials, and that was in 6.3. And if you look at the title of the thing, it's actually Taylor series. So that's exactly what we will do next time when we'll talk about this. So that's where this comes from. So we can see, could he be any number? So what was the center in this case? Well, c was 0 here, right? That was a special case. But we need the more general case. So this is how the more general case looks like. Okay. Now we want to go back to this problem here about when is it diverge, when it's converge. What does this mean? If you think about this, it means actually what we're asking for, if we want to think of this as a function in x. But the problem is you cannot put everything in there. X equals 1 is not allowed. So it's outside the domain of this function. But a half is inside the domain of this function. So the question on divergence and convergence is really a question about the domain of such a power series. Okay, so how are we going to do this? I'm going to work out a very general example because it helps actually better to see what happened, how things work. Okay, so here's an example of a power series. Summation, let's take 2 to the n. Sorry, let me try to write this a little bit more carefully. 2 to the power n, x minus 3 to the power n divided by n factorial. What is the an here? An is the part without the x's, right? So the ans is this part here. This is what the ans are. And then this is x minus c, x minus 3. So c here is 3, right? So the center is 3. Okay. Sorry, I want to get rid of a little bit of this drawings. Okay, so the center C is 3, and that we should always try first, whenever you get a series, the first thing you do is determine the center, which is very easy. And now we ask, when is this, for which values of x do we get a convergence series, for which one get the divergence? In other words, what's the domain of this function? So we think this of f(x) as a function. How do we do this? Well, we have several tests for convergence, and there is one test that we always going to use here. I say always. In the book they might do once in a while a different test, but always. Let's keep it that way. The test that we're going to do is the ratio test. So remember how that went. We have to take the limit for n going to infinity, and then there was this huge big fraction, right? In the bottom you would write the general term. Now this is the general term, including the x part. Okay, so let's do that. So I'll write 2 to the n x minus 3 to the power n over n factorial. And on top, the same thing, but replace n by n plus 1. Okay, so 2, this n becomes now n plus 1. X minus 3, not plus 1 here because it's x, not n. This is the guy that gets a plus 1. So n plus 1. In the bottom, n plus 1 factorial. Remember, use parentheses, otherwise it's not clear what you actually mean. And, very important this thing, there was this absolute values. Now you say everything is positive. Not really, because x minus 3, you don't know. If x is 0, you get negative 3, which is a negative number. So we really need to have absolute values here. Okay, let's try to work this out the way that we always have been doing, and really that's it. At this point, you'll see most of it is what you have seen already, although at the end we have to do something. Okay, so I'm grouping everything again. I'm going to rewrite everything. 2 to the n plus 1 goes in top. On the top also we get the x minus 3. Now, we know, I already just told you, the only thing that can really be negative is the x minus 3. So there I'm going to write, what is going on with this thing? It's jumping like crazy. You know. X minus, what am I doing? Is x minus 3 to the power n plus 1. So I'm putting x minus 3 between absolute values because that's the only thing that can be negative. This, of course, is positive. Okay, that goes there. What goes in the denominator? The n plus 1 factorial, which I'm going to write here, n plus 1 factorial. Then the 2 to the n is in the bottom. The x minus 3 to the n is also in the bottom. And on top, this guy, of course, goes all the way in top here, n factorial. Okay, let's simplify. We know how these powers cancel, right? This is 2 to the n plus 1 to the n, the highest power is on top, so we get a 2 there, right? That's a 2. And the same, notice, by the way, is true. Where did this come from? Sorry, there's this ugly line here, which I don't know where it came from. Okay, the same is true for these guys. They're also powers, right? So if you cancel them, the only thing left is an x minus 3. It's the same, it's just a different base. And then the factorials, I hope by now you know how to do that. Remember this n plus 1 factorial, we write it as, this is the biggest factorial, and we're going to write it in terms of the lower factorial as n factorial, and then that's not everything, we need one more, we have to go to n plus 1. Okay, so let me write it here. So we have an n factorial on top, and in the bottom we get an n plus 1 factorial. Sorry. That's kind of silly when I wrote down, because I already have a better. It's n factorial times n plus 1. So the n factorials cancel. And so we're left with the limit for n going to infinity, 2 x minus 3 divided by n plus 1. Now, if I plug in infinity, what do I get? Infinity in the bottom, that's 0, right? So I get 0. So what is the ratio test says? Oh, if it is less than 1, it converges. So what do you have? What is the conclusion here? We have a series that converges no matter what you plug in. Now, that's actually rather special. Most series will not have this property. And so I'll come back to this series in a little bit because it's more special than in general. So I'm going to do now one which is more typical. So here's another one. So summation, let's do x plus 4 to the power n divided by n. Why not? Okay. What's the center? Be careful. Look, in the formula to find the center, we have to subtract it. Okay. If you want, how do you find the center? Well, put this x plus 4 equal to 0 and solve for x. That's one way to say it. Another way to say it is that the center here is negative 4. Because x minus 4, that gives us the x plus 4 that we want. Okay. All right, so how does it work now? Well, same thing. We're gonna do the ratio test. to infinity. In the bottom we write x plus 4 to the power n over n. And in top, the same thing with n replaced to n plus 1 by n plus 1. And then we have absolute values. And these are very important, don't forget them. Okay, so limit n going to infinity. Let's put everything what we have. X plus 4, that's the only thing that needs the absolute values, right? Then I have an n plus 1. The n plus 1 goes in the bottom. I'm going to write it here because then this x plus 4 to the power n, again with absolute values, is going to be there. And then finally this bottom n goes up here. Good. Again, we have simplifications. This is power n, this is power n plus 1. The highest power is on top. So what we will do is we can simplify and we have an x plus 4 left. Okay, let me write up what I have now. It's the limit, right? But if you think about it, hey, what happened to my n here? Just this weird triangle came instead. So this was an n, right? So what we get here is, okay, let me write it up. Limit n going to infinity, we have the x plus 4, now always in the absolute values, and then we have an n divided by n plus 1. Now this has no n in it anymore, and the limit is with respect to n. Now remember, the limits, as far as the limit is concerned, x plus 4 is a constant. So we can take it out. X plus 4. And what is left is this limit here, n over n plus 1. Now, we know how to do this limit, and it's equal to 1. I hope everybody sees this. I'll do it quickly. Divide top and bottom by n. So divide by n, divide by n. So I'm left with x plus 4, and then limit for 1 over 1 plus 1 over n, which this last reciprocal here goes to 0. And so all in all, I get that this is x plus 4. So now what? Well, the ratio test. What is the ratio test says? What you need is something that's less than 1. But I don't know. Well, what is x plus 4? I don't know what x is. Exactly. So this now, so this is the thing. Ratio test gives the condition. It will tell me what is the condition. And the condition is basically what I just said, that this has to be less than 1. X plus 4 is less than 1. That's the condition for convergence. But the ratio test even says more. It says that x plus, if you're bigger than 1, then we have divergence. Okay? The only thing what the problem with ratio test is what happens what happens if x plus 4 is equal to 1? Ratio test, if you look back we go back to the topic, it says if the ratio is 1, then you don't know. Remember, in the book they call this rho. I don't use it that much, so sometimes I forget to write it, but I'll try to make a habit of it and writing rho. Okay, so the rho here, so we found rho was x plus 4, and then we have the three possibilities: less than 1, bigger than 1, and then this case that we don't know. Okay, so let's look at each of these three possibilities. X plus 4, less than 1. What does that mean? Well, an inequality, you can either solve it algebraically. You can say, okay, this means that I have that x plus 4 lies between -1 and +1. Right? That's how an inequality of absolute values means. That's this inequality, so I'm writing this up. And now I can solve for x by subtracting -4 everywhere. So I do -4, -4, -4, and so I conclude that this is -5 less than x less than -3. So we get here something that a range, an interval between -5 and -3. So if I put this on the line here, so here would be -5, here would be -3. Okay, and so our interval of convergence, this is what we know that here we have convergence. And we also know that outside we have divergence. But outside is exactly this condition, right? It's just the opposite of this. But what is this then? Well, this is exactly these 2 points. So these 2 points, we don't know exactly what happens yet. And so we will need to investigate it separately. I will explain this, but before I do this, I'm going to give you what I think is an easier and quicker way of finding this interval. I want to point out before I do this something that might seem a little bit of an accident, but let's look at the center. Where's the center here? It's -4, right? Where is -4 on the line? Well, exactly here, in the middle, in the center. That's why it's called center. And so, how far are we away from the center? Well, that is given by this number. And so this number we call the radius of convergence. Now you're going to say, wait. This 1 was from the ratio test, that's always going to be 1. No. The radius of convergence is, so what you do is, in general, here is a general thing, right? In general, we have a center. We have x minus c is less than r. So we get a condition using the ratio test, and we solve until we get an inequality of this type, and then this is what we call the radius of convergence. I'll do an example if it's not clear what I mean here. Right away. Okay. So the radius of convergence is 1. Now radius in terms of like if the radius of a plane, for instance, means how far it can fly. So this is exactly what it means. How far can you go away from the center and still be convergent? Well, the radius is 1, so you can go 1 to the left or you can go 1 to the right. And that's exactly where -5 and -3 come from. Okay, so that's another way of thinking about this inequality. They're both the same, but some people are more graphically and others like to solve things algebraically. But there's still one issue here. What about here? Well, that's the thing. So we have the radius of convergence, but we really want is, you see it's an interval, but we still don't know what happens in the endpoints. So the interval of convergence, the only thing we need is the endpoints of this interval. Now what are the endpoints? We see the endpoints here. X is -5, and the other endpoint, I'll write it a bit down here, x is -3. What do we do with them? Well, remember we have a series here, right? This is my series. Sorry, here's my new series, right? Let's call it f again. And what I need to do now is just plug in that endpoint and see what I get. So let's do that. So f of -5, what is that? Well, summation. It was x plus 4, right? I'll write it. X plus 4 to the power n divided by n, right? Let's see. I didn't say where I started from. I should have said it perhaps to be really completely correct. I cannot start from 0 because I cannot divide by 0, right? So that's what I wanted here. Anyways, that doesn't matter. So here we are. And so x is now -5. Sorry, I'm not completely done here. So this x now becomes -5. All right, in a different color here, -5. So what is that? What does it give me? Now I get a good old series, the one that we are used to. Because now the -5 plus 4 becomes -1, right? -1 over n. I kind of remember this. This is the alternating harmonic series. And I know that this is convergent by the alternating series test. If you don't remember anymore what it is, well, the alternating series test, what you need to do if you have an alternating series. Why is it alternating? Because of this one, right? So, alternating series test, what you need to do is you take the limit, you take the formula, but ignore the sign. So 1 over n. That's ignoring the sign. That's because that -1 to the power n, that is only plus or minus 1. And this limit for n going to infinity, of course, this 1 over infinity is 0, so this meant convergence. Okay. So this means this point is included. So I should have, okay, let me make my picture. I'm going to make my picture over again because it's now okay, so we have this interval, we have the center here. That was -4, we could go 1 there, that was -5, and 1 there, -3. We already noticed that we have convergence here, but we don't know yet what happens on the endpoint. Sorry, my color went a little bit more than I wanted it to go. So this one is now included, so I'm making it dark here. What about x minus 3? Well, let's plug in. Now we do the same. What is f of negative 3? That is, oh, sorry guys, I'm gonna have to stop soon because my pencil is almost out, but okay. F minus 3, what is that? That is summation minus 3 plus 4 to the n, right? Again, instead of minus 5, I have now minus 3 over n. But 4 minus 3 is 1, and 1 to the power n, what is that? Think about it, it's just 1, right? So I get just a harmonic series. And that one, we know, is divergent. Why? Because p is 1, p series. So what does this now mean? That means that this other point is not included. Sorry. So it's an open point. Okay? And what about the outside parts? Well, we know already this is divergent. These are the divergent parts. So this is this is divergent, and the blue is convergent, including this point, but not including that point. And that is the general picture. So that's how it always will look like. It's always going to be an interval around the center. Now, what about this first case where this was 0? What does that mean here? Well, let's make the picture for this one here. So I'm going to do the picture here. Plus the center was 3, right? And now it says you can, as far as you want to go, you're convergent. So the radius of convergence here is infinite. It doesn't matter. As far as you want to go, you're okay. And therefore, so we have the interval of convergence here is just the whole entire line. Now things can be bad as well. Here's an example of things that are really bad. So I'll do another example. Let's do this one here. Let me take one. Summation n factorial x to the n. Okay, let's look at this case quickly. So what do we need to do? The center is 0 in this case, right? Take an easy case, ratio test. Okay, the limit for n going to infinity. N factorial x to the n. Here we get an n plus 1 factorial x to the n plus 1. All right. We are already right there, right? N plus 1 factorial. I'm gonna remind you, this is just n factorial times n plus 1, and it is above. So the n factorials cancel. These guys cancel. Also, the powers of x cancel except one power remains, right? So we have an x left. Now, don't forget there is an absolute value sign, right? So we have n plus 1 and also absolute value of x. These are the two things that remain on top, and there's nothing in the bottom. Okay, what is the limit here? Well, this x, I can take it out because it doesn't depend. That's always something you want to do. It doesn't depend on it. But then, that's infinite. And that, infinite radius of convergence. No. This is the ratio test. And the ratio test says it has to be less than 1. This was rho. Now, infinity is never less than 1. No. So this is always divergent. Always divergent. Well, that's not entirely true. So what does it mean? So if it's always divergent, that means that the radius of convergence is 0. That's for sure, right? You cannot go away from the center. But notice in the center, I can still plug in the center, right? If I plug in 0, well, everything is 0 except for the first term, the constant term. So the picture now is we have the center here in blue. We have a 0, but everything else is divergent. So we have divergence here, and we have divergence that way. So, yeah, divergent. Okay? So this is the opposite, where we have radius convergence 0, we can have radius convergence infinite. But these are special cases, and the most general case, and you're gonna probably get something like that, is the case where we have halfway. Okay, so that's our first part. I'm gonna assign some homework problems on this, and then we need to do some more problems, but I'm gonna put some more in the next video. part 2, I'm keeping them a bit separate because they're slightly different things that we will do. But I'm going to give you an example in the next video. I'm just afraid that my pen is going to run out, and then okay, so don't forget to watch the next one.